Okay, so one of the big expectations in the grade 10 course for students is trigonometry, and trig is kind of that big scary word that a lot of people seem to think, wow, that's pretty serious stuff, but really trigonometry is related very closely to similar triangles. So I've drawn a couple of triangles here. I've drawn a triangle that has lengths of 3, 4, and 5 centimeters, and the angles are shown here. We have a 37-degree angle in the bottom right, 53 in the top left, and then a right angle at the bottom. And then down here we have another triangle with 6 centimeters, 8 centimeters, 10 centimeters, and the angles again are 37, 53, and another right angle. So first of all, to identify these two triangles as right angles, it's important for us to realize that right angles have to be similar, and that means that their angles would match up. So we have 53 degrees here, we have 37 degrees down below here, again 53 here, and 37 degrees here, and then they both have right angles. So as long as you have the same angles in your triangles, you're going to have similar triangles. Now, I happen to have these measured out so that the small one is exactly half of the large one, but they don't have to be. As long as you have the angles matched up the same, I could have chosen any proportion I wanted to demonstrate this, but just for the sake of this example, I kept it at double. So what you'd want students to realize is that if I have similar triangles and I take two sides, for example, I take this side down at the bottom here, the 4 centimeter and the 5 centimeter, I divide those. So I'm going to divide 4 by 5. I end up with 8/10. And if I do the same thing down here with those same two sides, like the same side, the similar sides in the triangle, we have 8 and 10. And if I divide those, I have 8 divided by 10, and that is also 0.8. So that number right there and that number right there are going to be the same if the triangles are similar. And if I repeat that process with other sides, I would see again that here, if I divide 3 by 4, for example, 3 divided by 4 is 0.75. And again, down here, if I did the 6 and the 8, 6 divided by 8 is 0.75. And then finally, let's do 3 divided by 5. So if I do 3 divided by 5, that number is 0.6. And then down here, 6 divided by 10 is also 0.6. So it's not surprising they're all the same because those triangles are similar. When we get into this trig, this sine, cosine, and tangent, students get all kind of frozen up. Part of the problem with that is that when you go to a calculator, and this is an iPad calculator, so it's pretty complicated, but your scientific calculators usually aren't much nicer. If I want to know sine, cosine, or tangent of a value, I'd have to punch in sine of 60 degrees, and it'll shoot me back some kind of random decimal number. Now that random decimal number is what sine of 60 is worth in degree measure. However, students have a hard time getting a context for what that number actually means. But if we come back to this for a second, all that number is telling you is that if you take two of these sides and divide them, for example, here we had 3 divided by 5 and we got back 0.6. This number is simply a ratio of two of the sides in our triangle. But again, the problem with the calculator piece is that they have a difficult time making a connection. And sometimes we have to kind of go backwards a little bit and put the technology away. So I'm going to turn this off for a moment. And we're going to look at another tool that our student with a processing speed difficulty may appreciate. So this is a trig table. Trig tables were more popular back when there was no technology available. But what this trig table gives us is it gives us an angle measure, and it gives us sine, cosine, and tangent values. So basically, if I drew a triangle that had an angle of 1 degree, that's the one right there, and I divided, now the sine ratio is opposite divided by hypotenuse. But if I did that, I'd end up with that decimal. So if I divided the opposite by the hypotenuse for a right triangle with a 1 degree angle in its corner, you'd end up with that as its value. The same way that when we divided over here, let me just pull this back out again, when we divided over here, we ended up with these values. This is what you would end up. Now all these are the ratios of the sides for triangles. So there's the cosine ratio, which was adjacent divided by hypotenuse, and the tangent ratio, which is opposite divided by adjacent. So getting into all the trig, a tool like this where students can see how these numbers increase. The sine value starts at 175 10,000ths, and then increases and goes up and up and up and up, and is always increasing up to the point where if we travel over this side, here's 46 degrees. If I go all the way down here, the sine ratio is almost at 1. I mean, 998 10,000ths, sorry, 9,998 10,000ths. And similarly, sometimes seeing the big picture and seeing how all these numbers kind of connect with one another and where they show up is important. And we can also show students that it's not really all that scary. So for example, our 37-degree angle over here, if I go to 37 degrees on my trig table, which is right here, we'll see numbers that we just witnessed. I'll wait for that to focus in. Are we going to focus? Maybe I'll pull up. There we go. So here is your 0.6. Here is your 0.8. And here's your 0.75 that we witnessed over here as our value. So sometimes it's about making those connections with students and maybe putting the technology away. And a tool like this, again, easy to find trig tables. You can use them with students who have LD. You can use them with other students in your class. And I've actually seen students who don't want to use their calculator. They can just look up the values on these trig tables and have the answers right away.